Okay, so I want to look at the 11th problem on our review activity. This problem is a little bit more mathematical than anything that we will see on the midterm, but it's a good exercise to recall Fick's first law. So the 11th problem says, derive an expression for the flux of a monodispersed population of particles to the bottom of a container if both Brownian diffusion and settling are at play. So we're looking at some sort of vessel like this, and we have particles that over time are settling out, but also subject to Brownian diffusion. So we have some sort of vertical coordinate, we can call it z, and at the top of our vessel, then the number concentration n is 0, and at the bottom of the vessel, which is a vertical distance b, we have a number concentration n sub b. Those are our boundary conditions for a differential equation that looks like this. So J is the flux of our particles, and we have one component of that flux that's dictated by Brownian diffusion, and a second component then that's dictated by settling. So I should use a capital N for consistency's sake. Particles are also being carried downward by their terminal settling velocity. We've assumed that they're monodispersed, so we only need one of those terminal settling velocity values. We can kind of check, right, that all three of these terms have the same units. This J is a flux, particles per square meter per time. Then this is a diffusion coefficient or diffusivity that has units of meters squared per second. The concentration gradient in our particles, right, is a number concentration, so particles per cubic meter divided by some sort of length scale, z. And then this last term, the settling term or sedimentation term, is a velocity times the concentration, number concentration of our particles. Right, so each of these terms has units of particles per square meter per second. So then what we want to do is to solve this differential equation that's in star. So we want to separate our variables. I want to get everything that has an n on one side and everything that has a z on the other side. And start by kind of rearranging the terms and then putting everything that has an n over here on the left-hand side, and our diffusion coefficient and our dz on the right-hand side. Should be 1 over d, sorry. Okay, so now we're going to integrate from top to bottom, so on both sides. So at the top, right, at z equals 0, we have a number concentration that equals 0. And if we integrate then to the bottom, z equals b, then we have a number concentration that's n sub b. Anything where we have a form dx over x gives us a natural logarithm of whatever's in the denominator. And we have to multiply by 1 over whatever the prefactor is on our dependent variable. So I have to evaluate this then from n equals 0 to n equals n sub b. On the right-hand side, then we're going to do the same thing. The integral of dz is just z, and we have to evaluate z from 0 to b. So then we get the logarithm of j plus vts over n divided by j. Right, if I plug in n sub 0, then the second part of the summation goes away. And a difference of logs is a log of a quotient. So I've just used that log property from here to here. I'm going to multiply this vts on the opposite side. And we're going to evaluate z from b to 0, which is just b. Okay, we have a little bit more algebra to do here. We need to take an exponential of both sides. We're solving for j, right? We wanted the flux. That's our end goal. So J over J is 1, and VTS over times N over J is this exponential. And really from here out, it's just algebra to rearrange stuff in order to get an expression for J. I'm going to flip everything. So now J equals minus VTS over N divided by 1 minus. Hopefully I'm still on the camera. It looks like I am. And this is then our final expression for the flux, given that there's both Brownian diffusion and settling in our vessel.